Okay, so last time we just kind of talked about the very, very broad strokes of Section 5.5, change of variables, and I should remind you 5.5 is massive. It's going to be, at least 2, probably 3, pushing 3 anyway, class lectures. So just the first part of it is what we've sort of scratched the surface of. And I want to hit those highlights again real quick. I want to remind you of the substitution rule that I know that you know, right? But in particular, I want to take this specific point of view on it. I want to think of the the substitution function, which we will soon reconceive of as something called a change of variables function, and thus my verbal stumble. But the substitution function, I want you to think of it not as an algebraic thing, but as a geometric thing, as a function that literally takes points from a domain in the t-axis and returns it to as a point on an interval on the x-axis. And with that in mind, notice that this interval from A to B turns into this interval from G of A to G of B. And there are 2 key aspects of how this equation kind of comes out of this geometric point of view. First is the idea of a pullback. So it's weird to think of a function that goes this way as actually turning around and doing something that goes this way. But it does, because, again, come up here with some extra space and point out that if you have a function, for example, that gives, let's say, x is, t cubed minus t, something like that. You give me a t, out comes an x. The function clearly goes from the t-axis to the x-axis. But what does this function do to expressions? Not to points, not to values, but to expressions. Well, if I have some function of x, if I have, cosine of x, that expression can be rewritten in terms of t just by plugging in. Because after all, x is t cubed minus t. You just pop it right on in there, right? And weird though it may seem, while the function pushes forward, expressions pull back. Right? So this is one of the big ideas here. And I claim that happens not just to algebraic things like cosine of x or whatever, but any expression such as, for example, an integral. Right? So what I want to think of this as is what this function g does. Its job as a substitution function is to take an integral in what you might call the output space and pull it back to turn it into instead an integral in the input space. Does everybody believe it? Is that cool? Is everybody happy? Okay. Most of this is just plugging in. Not that much to it, really. So per the previously noted example, if x is g of t, then, well, this x is g of t. Just plug it right on in, no problem. Right? Okay, the second thing, though, that I want to talk about is this idea of a stretching factor. The idea of a stretching factor is, again, we have an interval on the t-axis. Its image is a different interval on the x-axis. And along those lines, each subinterval on the t-axis will also have an image. It will have an image that is a subinterval on the x-axis, whose size, of course, is dx. Right? And so now what are we going to do about that dx? We want to rewrite everything in terms of t. We're doing this pullback. How are we going to rewrite dx in terms of t? And yes, you can make this sort of algebraic argument here about, that's somewhat notation dependent. And okay, I guess you could do that. But let's, again, for the purposes of preparing ourselves to adapt this tool to a multivariable setting, let's take a different point of view. And let's think of this dx here not as a distance. Let's think of it as a change. Let's think of it as a output change. This represents how much the output to G changed as I changed the input by dt. Right? Remember, if you have an input change, there is a corresponding change in the outputs. And what is our relationship between input changes and output changes? Well, the derivative. Right? This is, again, one of our fundamental points of view on what a derivative is. So, with that in mind, you can think of this not as sort of algebraic notational manipulations or anything like that. This is what the derivative does. Our derivative here stretches out a little piece of interval on the t-axis and turns it into a little different sized interval on the x-axis. It's how much that piece of the t-axis gets kind of pulled and stretched to become, well, at least in this case, as I've drawn it here, gets stretched out to become bigger. What do you think? Is everybody buying it? Okay, so again, a lot of this is old news, arguably new takes on old formulas, stuff that you already understood. But again, the take is critical, because what we're going to do is we're going to try to adapt this point of view on the substitution rule now to a multivariable setting. So morally not that different. It's in terms of the details, yeah, absolutely. Now I've got a two-dimensional domain, and I'm talking about a multivariable function that then spits out points that are in a two-dimensional target. Yeah, that's very different, but it's still, we have an input space and an output space. Still, I can talk about what does this domain, if I have literally a rectangle, let's suppose, in the input space, I can talk about what the corresponding output, the corresponding image looks like, and it'll, of course, be changed in any of many different ways. It might be moved or turned or stretched or bent or twisted. There's lots of different weird things that can happen. So notice I've drawn something deliberately, weird and undesirable. Okay. Is that cool? Is everybody happy? Yep.
Is that second picture like in 3D space, or is this just a 2D?
No, 2D. Yeah, 2D. So this is a function from 2 dimensions to 2 dimensions. Absolutely. In fact, when we're talking about what we will call change of variables, the input and output dimensions kind of have to be the same. Yeah. There is a version of this where they're not the same, and we'll talk about that later as well. But we have to take a very different take on that. Okay, so again, we can kind of take the ideas that we just talked about and ask, how do they manifest in this two-dimensional context? And well, there's still the idea of a pullback. I can talk about an integral whose domain is this output, this image domain. Right? And if I have such an integral that I want to compute, it will presumably pull back. Just like in the single variable substitution case, right? Expressions pull back, points push forward, domains, sets push forward, expressions pull back. So, okay, well then it's gonna turn into some integral over here that takes place on our original input domain. And so the blue integral on the right is going to turn into the green integral on the left. Again, a lot of that's just plugging in. Plugging in is no big deal. The whole point to this function, after all, is that x and y are this g function of u and v. So that's just plugging in. Whatever the formula is for x, plug it in. Whatever the formula is for y, toss it in there. No problem. The delicacy, again, is what happens to pieces of area. Again, we've got this little piece of area here. That's the output. That's what comes out when you put in this input little piece of area there, that little subrectangle. Green gets turned into blue. The way I have it drawn in this picture anyway, looks like the blue one's bigger. How much bigger? Right? That blue, whatever shape that is, can't assume it's going to be the same size as the input green subrectangle. Why would it be? So there's going to be, again, a stretching factor. This output this little piece of the output domain is going to be some factor multiplied by the area of that little piece of input domain, which of course is a little subrectangle, so du dv is what that area is. And if I want to know how much bigger is the output than the input, I'm going to have to try to figure out by what factor has that area been increased. And that's what we're going to call the stretching factor. And how to compute that is something we'll talk about a little bit later today, hopefully, fingers crossed, stay on schedule. But for the moment, I'm just going to tell you the formula. There's enough going on as it is. I don't want to get distracted by, computation. I want to just, keep the focus on the concept of the pullback, and the concept of the stretching factor, and then we're going to start doing examples. We'll come back to prove the formula. Here's the formula for the stretching factor. The stretching factor is the absolute value of the determinant of the derivative matrix. So it turns out. For the moment, take my word for it. A couple things to say about this. First of all, don't forget what the derivative matrix is. The let's see here, color choices. The derivative matrix here is a matrix of partial derivatives. Okay. Next thing I want to say about the notation is this expression, and specifically I'm talking about the expression inside of the absolute values, not including the absolute values, just inside it. So the determinant of the derivative matrix, very often written like this, partial xy, partial uv. That will seem, I would imagine, like a pretty weird notation. Let me talk about why that's reasonable. It's reasonable for a combination of reasons. First of all, notice we are taking the partial derivatives of x and y. So, partial x comma y at least kind of conjures, is kind of suggestive of that we're taking the partials of x and y. And we're taking those partials, you can see right here in the formula, with respect to u and v. So this notation, partial xy over partial uv, vaguely anyway, kind of suggests that derivative matrix. Is that kind of okay? It's just notation. We don't want to overthink it. Why haven't we used this notation before? Well, we haven't really talked about the determinant of the derivative matrix before. I think this actually wouldn't be a good choice of notation for just the matrix itself, because after all, the matrix is a matrix, and this here kind of looks like I've written it as a fraction. That really makes it look like it's a scalar, and having a scalar looking notation to represent a matrix, kind of weird, right? So in what sense is there a scalar here? Well, of course, determinant of the derivative matrix is a scalar. So that kind of fits as well. But here's the really beautiful thing about it. This is the main reason that I love this notation here for the stretching factor, is as follows. Let me actually rewrite what we have here with the stretching factor in there. Partial x comma y, partial u comma v, like that. There's my stretching factor, apparently multiplied by du dv. Right, and the claim is that is equal to this thing, which is, of course, dx dy. It represents area in the xy plane. So altogether, we're making the assertion that is equal to that. And look at this. It kind of looks like that cancels with that. Now, it doesn't. That's a horrible math crime. That's not a thing. First of all, that's not a fraction. Second of all, the denominator doesn't even look exactly like the thing I'm canceling it with. There's a long list of reasons that this is, this should kind of freak you out just a little bit. It's not okay mathematically, but it looks great. right? I mean, it looks like a vaguely reasonable cancellation, and then X's and Y's are what's left. It's kind of nice in that way. At a minimum, it makes for a nice memory tool. So anyway, that's another reason why I like this notation. Okay, let me pause. How are we doing? Is everybody on board? Questions? Feel free. No? Yeah. Oh, no, I'm sorry. I thought, yeah, okay. Anybody? Okay, so we're going to use that notation a lot. And let's do one. Let's dive in. So suppose we want to compute this integral right here, taking place on this domain right here. How am I going to compute that integral? Very first thing I want to observe, this looks like a nightmare. The integrand's not bad. X plus y, that's cool. It's a polynomial. But check out that domain. It's got corners everywhere. Right, so no matter which way you slice, this is going to look like I'm going to have to break this up into three separate integrals. Like if I were to slice, first horizontally, 1, 2, 3 chunks. So I don't want to do that. That stinks. And then if I were to slice vertically instead, well, then again, the corners get me, and I have again 3 chunks. So this looks pretty undesirable. Okay. All right. So what we're going to do instead, and in this statement of the question of this, this first example, just to get us off the ground, just to get a win under our belts, I am explicitly giving that this domain is, in fact, defined as the image by way of a given function of a given pullback. Right, that's free information for the purposes of this example. Now, you might be thinking to yourself, well, that seems a little too good to be true. Are we always going to be just given the pullback domain? No. Are we always going to be given the change of variables function? No. This is just a starter example, again, to get us off the ground. Let's get a win under our belts. Okay. All right, is everybody clear on what the statement of the question is? Okay, so again, we are given an integral over here on a domain that we don't like, and what we're going to do, big surprise, is pull back to an integral over here, which of course is a rectangle, which we do like. That's everybody's favorite domain for a double integral, I would imagine. Okay. So, how do we do the pullback? Well, we use the formula on the previous page. We are going to do this pullback by plugging in for X and Y, for whatever they are, and by remembering also to compute and insert this stretching factor in recognition of the fact that the pieces of area on the right are not the same size as the pieces of area on the left. So, starting off with the stretching factor, here's my Jacobian matrix, aka derivative matrix, sometimes called a Jacobian. So there it is. I know I need to compute the determinant. Specifically, the determinant is what this notation here means, and again, I love that notation. And a little bit of algebra to do, multiply it out, and bam, there you go. There's your Jacobian determinant. Anybody follow that part? Now here's a tricky bit. I'm going to have to figure out what to do with the absolute values. Very importantly, the stretching factor is not the Jacobian determinant. The stretching factor is the absolute value of the Jacobian determinant. And there's a good reason for this, and it has to do with the fact that when you look at what a function does in taking a region of a domain and bringing it over into the target, is it might stretch it out or rotate it or shear it or any of a number of different things, but it also might flip it backwards, and it might, I can't do that with two hands, it might flip it over upside down, and that'll make the determinant negative, as it turns out, but it's still area, and it still counts as positive because it's still a piece of the domain, and we don't want that minus sign in there. So we have to take the absolute values. So how do we deal with the fact that we've got to deal with these absolute values? And in particular, then, what is the absolute value of this thing that we just got through computing? And it looks concerning. It's not immediately clear. By the way, to make sure you are comfortable with the algebra of absolute values, you can't just kind of separate that into the absolute value of two separate things and subtract them or add them, or I don't know. This doesn't work, right? So we have to deal with this in a different way, and there is key information on the screen that resolves exactly how to deal with this expression. It's hiding. The key information, though, is I can see on the screen right now what u is doing. And here it is. There's my u-axis. So there's the range of values of u. It says right here, given that my pullback domain is this, I can see in the picture, u apparently is always between 0 and 1. Right there in front of us. Does everybody see that? Is everybody happy with that? Likewise, I can see right here in front of me what V is doing. V is, well, there's the V-axis. And so V apparently is also always between 0 and 1. So just looking at your pullback domain gives you a tremendous amount of information. And now I can kind of piece it together. That means U times V is always between 0 and 1. That means 4 times UV is always between 0 and 4. Is at most 4. And then altogether, when I subtract 9, that's clearly negative. Right? So for all values of u and v in our pullback domain, for all practical purposes then, this thing inside the absolute values is always negative. How are we doing there? Okay. And neat fact to make sure you remember from high school algebra, the absolute value of a negative number is the negative of that negative number. And I hope that's cool. I mean, that's when you want to, sit down and think it through. And the more you think it through, the more you'll realize, yeah, of course it is. That's just how absolute values work. Okay. So I just take the negative of it. Now, before I proceed, I want to recognize every question's going to be different. It's not always going to be that the pullback domain will be this. So you can't just always assume u and v are between 0 and 1. No, absolutely not. Right? And it won't always be that you have the two terms, and it won't, it's just going to be different with every question. So this is just a for example, right? You got to treat every example individually. But this kind of thing is what you want to be thinking of. Yes?
So what would we do if it alternated? It's like in this example, I guess
yeah.
The square would be like a 3 by 3 square.
Right. So for example, it could end up being that that there's a line or something right there, and that the expression in question is positive on that side of the line and negative on this side of the line. And I'm sorry to say, what you would have to do then is break it up to two separate intervals. Because, the absolute value must be dealt with. And over here, the way you deal with the absolute values is by throwing them away, because you're taking the absolute value of something positive, and so you just toss them. Whereas, over here, you're taking the absolute value of something negative, which means that you have to throw in an extra minus sign. And so, yeah, two separate intervals, and that'd be unfortunate. Keep in mind... I think if you were to look back through my old exams, you would notice a pattern on how often this does or doesn't show up. Not saying anything official there, but you can speculate based on the data there. Yeah, right. Is that cool? All right. Okay, so it's all over but the shouting at this point. We have our original integral in the xy plane. We do the pullback. Let's see, I'm going to need to, how much of this can I fit on the screen? Okay, I'm going to have to zoom out a notch. Here we go. Step 1, start plugging stuff in. What is x? Apparently I'm going to need to plug in for x that I see in my integrand. Oh, here it is, x is apparently that expression. So x is that. And now elsewhere in my integrand, I see a y. What is y? Well, y apparently is that expression right there in the formula for the change of variables function. And so y is that expression. And therefore this integrand, this original integrand, x plus y, gets rewritten just as that. I mean, you're literally just plugging in. Really very little happened there. The only, I guess I'll say the big takeaway, the big moral on this point of the problem is don't forget that your change of variables function explicitly tells you how to do the plugging in. That's what the change of variables function is, in fact. Is that satisfying? All right. All right. So what about the stretching factor? Well, we went to some trouble already to compute that thing. Our stretching factor is apparently 9 minus 4uv, so don't forget to toss that in there. That makes my dx dy something I can rewrite in terms of u and v. And lo and behold, we're done. We have ourselves a brand new integral. Right? We have successfully turned this integral that, again, I claim we don't like. Not because of the integrand. Look, the integrand's actually pretty nice. I like that integrand, but I don't like this domain. Right? But I've now turned that into an integral that at a casual, superficial glance you might not like so much because, after all, it's got bigger polynomial on the inside there. But our domain here is a unit square, everybody's favorite domain, constant bounds, right? It's really nice. So much more desirable integral to compute. Everybody cool? Yeah. All right. So this is the big idea, change variables. For whatever it's worth, this is one of the biggest ideas in the course. The idea of a pullback and turning one integral into a very different looking integral on a very different looking domain. And this has just extensive, powerful applications because in the real world, we very often find ourselves looking at stuff like that, over which we need to compute integrals, and which we really, really don't want to have to deal with. And so we very often will pull back through a change of variables function and find ourselves instead looking at an easy integral. Okay. Big point. Related, this is going to be one of the big ideas behind various different computational tricks and constructions that we're going to define. We're going to define something called integrals in a coordinate system. Fundamentally, this idea. We're going to define something called a line integral once we get into Chapter 6. Fundamentally, there's other fundamentals involved in there as well, but this is one of the big ideas, really, you get right down to it, in defining a line integral. And likewise, this is one of the big ideas in defining this thing called a surface integral that will figure very hugely in Chapter 7. In fact, if I were to, I've heard people talk about, when you're designing your course and your syllabus, you should always have in mind, a very short list. For example, 3 big points of the course. And I think this would be one of them right here. Okay. All right. Okay, so now I kind of cheated in that last example. I created an example where the change of variables function was given. Will it always be given? No, we already delivered that. Bad news. So you are going to have to think up, in most cases, your own change of variables function based on what kind of a domain are you looking at, what do you not like about it, and how do you want to fix it, right? So here's some examples of things that you can do. Before I get into the list, let me point out, again, there is this sort of backwards factor, right? Whatever the function does, the act of pulling back, in some sense, you're moving backwards through that function. So there is a kind of an undoing, kind of a reversal aspect to how this works, and I'm going to show you an explicit example on the next page. But if you translate, if your change of variables function translates by a vector AB, when you pull back, effectively your domain is going to get shifted, well, backwards, and thus is going to get shifted by negative A, comma, negative B. And likewise, a stretch will turn into a squish. And a counterclockwise rotation will effectively accomplish a clockwise rotation. And this is the one I'm going to give you an explicit example of on the next page. Let's do that. Here it is. I've got a domain D. It's a square with certain corners given. Here's that square. And on that domain, I want to compute an integral. And I'm going to, again, label this with a sad face because I don't like this domain because, again, I keep hitting corners when I go through and start slicing, right? If you slice horizontally, you hit a corner and then another corner. And so we're going to have to do 3 chunks. Nobody wants that. Or if you slice the other direction, well, you hit a corner there and another corner there. Again, 3 separate integrals. Nobody wants that. Okay, so how do we avoid it? So the big idea, I'm going to point out that this is what you get when you take the unit square. Yeah, whoops, highlighter. When you take the unit square in the UV plane, and if you rotate that unit square counterclockwise. Sorry, not unit square. I'm sorry, I misspoke. Square of radius 2. This side length is pretty easily computed to be 2. Sorry, I misspoke. Okay, so this you might say ideally oriented square. Rotate it counterclockwise, and you get this awkward, unfortunate square that we're actually dealing with. Now, I say it's counterclockwise just for sort of the visual effect. Let me point out this is kind of what you might think of as the original square, and notice that it is literally a counterclockwise rotation. That's what our T is. This rotation that turns the yellow square into the blue square is counterclockwise. Is everybody good? Of course, now just to foreshadow, why are we viewing this square as a counterclockwise rotation? Well, because when then I pull back, I will effectively be turning an integral on this undesirable square. I'll be turning it into an integral on my more desirable, lined up with the axes square. So the counterclockwise rotation, pulling back, will clockwise rotate the blue square into the yellow square. Okay. All right. So we're going to need to know what this function is. What is this rotation? I'm going to remind you again. I said at the start of the course, and it's been you've been seeing this play out in several examples, but linear algebra is going to show up quite a bit. It's a prerequisite for the course. And remember, one of the big aspects of linear algebra I need you all to be really comfortable with is that rotations and reflections and other transformations in the plane, but rotations in this example in particular are linear transformations. Linear transformations are represented by matrices. Matrices are understood by their columns, and the columns are the images of the standard basis vectors. Right? So this sort of like sequence of 4 thoughts together is going to allow us to find what this rotation matrix is, and that matrix is this, as it turns out. Now again, I'm leaving the details for y'all to think through. You've probably done it before, but anyway, make sure that you're strong and comfortable with that calculation. I've written this, you'll notice, in terms of this angle theta, and theta, you can do a little bit of geometry and persuade yourself based on the given points. Theta is pi over 6, and that turns the matrix then specifically into that. A lot of linear algebra happened there. Come to office hours if you have any questions about it. I'll be happy to walk you through it, but I just want to make sure that everybody is comfortable and proficient with how to do that. Okay. All right. Cool. So we have ourselves then a change of variables function, and here it is. T of uv is x comma y, and it's computed by that formula. Everybody happy? Okay, so, well, let's see here. I'm going to need to compute my Jacobian determinant, aka partial xy, partial uv. Determinant of those partials. There's the derivative matrix. Take the determinant, multiply it out, and interestingly, you get 1. That's nice. That's weird. It's an eyebrow raiser. How come? What are the odds? I see square roots and fractions all over the place. How did that turn out to be 1? And then you think to yourself, well, wait a minute. This linear transformation here is literally a rotation. How much do rotations make things bigger? Not at all. It's rotate. So this is not actually weird. This is actually highly expected. Right, but anyway, it's just kind of interesting how sometimes things work out nicely. Lucky break. I do want to point out that for the purposes of this course, I do want to actually see the calculation. Again, if you think about it, the purpose of a question of this sort is to make sure students are proficient with the methods of change of variables, which in general require doing this calculation. So I do want to see that calculation on an exam or on a homework exercise. Outside of Math 219, no. Outside of Math 219, you can just make the case. This is a rotation. There's no stretching factor. Right? It's geometrically obvious. Okay, and now it's, again, all over but the shouting. I just gotta, first of all, insert the absolute value of my Jacobian determinant as my stretching factor. No problem. Absolute value of 1 is 1. Then I gotta start plugging stuff in. Let's see here. What is x? Well, x, there it is. First output from my change of variables function, and it's this dot that, aka that. Right. And let's see, what is y? Well, there it is. There's y. So this dot that is that. Right? So my original integrand, 2x minus y, is now 2 times all of that stuff minus all of that stuff. Right? Just plug it in. Nothing happened. Again, the main thing that happened, I suppose, is appropriately interpreting the change of variables function as giving me explicit formulas to plug in for x and y. Just make sure to remember the change of variables function is that thing, right? That's the action of plugging in. And it's all over. We've got ourselves an expression that you can simplify it a little bit. Our pullback domain, of course, the whole point of this is that I wanted to have this much more desirable pullback domain, this yellow square, which in the UV plane has super easy bounds, and we have turned the original integral, ugly original integral, into a much easier integral. What do you think? Big point on this example is I did not have to assume the change of variables function. Here we strategically chose our own change of variables function based on looking at the domain and seeing what would be convenient. Okay. All right, now a couple of little detail observations. These things have to get said. Technically, in order for everything that I'm claiming here to actually work out, we do need the change of variables function to be continuously differentiable, and that's just a formality. It's nothing to worry about. You also need it to be invertible, and this is a sticky little wicket that comes up as follows. If you, let's see here, if you have a function that is not invertible, you could end up with the following. You could have a domain in the UV plane whose image in the XY plane, let's see if I can draw this now, might do something like this. It might fold over itself. And then you'd kind of be double counting in that intersection. So, okay, so this is annoying. Most of the time you don't need to worry about this, but technically, just if something goes terribly wrong, you might, in some other context, you might look for whether maybe something horrifying like this might have happened. Okay. All right. Okay. Another observation I want to make. As it turns out, if you have a UV space over here and XY space over here, and over here you have some undesirable domain over which you're doing an integral, and you're hoping to be able to find a change of variables function through which you can pull back, right? That's what we've been doing so far. So we'd really like to be able to find this function. Sometimes it turns out that that's really hard to write down. But it might be much easier to get a function going the other way. Now, can you do that? Is that a thing? We do have to adapt some things accordingly. But if you look back at our statement about change of variables, this is, after all, an equation. An equation does go both ways. If A equals B, then B does equal A. So, we could write down an equation. We could actually make use of a function that's going, you might say, the wrong way. And sometimes, again, this is just the only thing that we can write down algebraically, sort of feasibly. So how do you deal with that if that's the case? Well, I'm going to point out first that if you look at this function, x and y are functions of u and v, and as a change of variables function, there's the stretching factor. And if you then instead look at this function, now forget about all what's happening up here. Forget about the original integral that you had. Just think of, we have output variables, now u and v. Input variables, now x and y. This stretching factor, going this other direction, well, it's going to be partial uv, the partials of the outputs. U and v are now my outputs, with respect to my inputs, and x and y are now my inputs. So, alright. So I have two different functions and two different stretching factors, and, I point out, modestly here, that if you go over to the right and then back, nothing happens. Right? Altogether, the composition of these two functions is nothing. Nothing happened. Nothing changed. So altogether, this overall stretching factor has to be, of course, 1. Input area, you go over to the XY plane, you come back to the UV plane, you have exactly the same area you had before. And so therefore, then, the product of my two individual stretching factors has to be 1, and therefore, each is the reciprocal of the other. Now, there's a temptation to look at this and think, well, yeah, of course, because these are fractions, and when you take a reciprocal of a fraction, the numerator and the denominator switch, right? Very, very tempting, but make sure to remember that's not what this is. You've got to remember that, let's see, where is it? Yeah, this is not a fraction. That's a lie notation. It's it's abusing the notation of a fraction. It's not a fraction. It's a determinant. So, not a fraction. So anyway, so this is a non-trivial fact when I claim that when you go the other direction, the stretching factor is just the reciprocal of the other stretching factor. But this is another arguably good reason that we like this notation, is because This is another example of how this thing kind of behaves like a fraction. It's again not good reasoning, but it is good, convenient sort of memory tool, and makes life easier that little bit. So yet another reason to use that notation. Here's a circumstance where this might come up. Suppose that you have a domain R. That's this thing in here. And it is bounded by, you'll notice again that terminology. Let's see here. These two equations, xy equals 1. Missed. And xy equals 2. Wait, am I? I keep missing. Sorry. Xy equals 1. Keep me honest. And xy equals 2. There we go. And then these two equations, xy squared equals 3, and xy squared equals 4. So 4 equations there, and, well, there is a unique region bounded by, in the first quadrant, bounded by these 4 curves. And let's suppose that's our domain. Weird. So not only weird, though, but full of corners. Right? There's a corner there. There's a corner there. I think you can see no matter how you slice this, you're going to have to break this up into 3 separate integrals. Again, highly undesirable. Nobody wants that. So does everybody see the context here? By the way, just in case you think I might have made this up, this example, not really. I want to let you know where this comes from. Y'all are engineers, and y'all are going to eventually see something along these lines if you take a course in thermodynamics. Thermodynamics involves, well, there's a lot of stuff in the course, of course. One of the things they talk about is something called a Carnot engine, or a Carnot cycle. So I saw this in a physics thermo class. But it serves a very important sort of theoretical purpose in thermodynamics, and computing the efficiency of a Carnot engine involves describing the process that the Carnot cycle goes through in a plane. It turns out that Carnot cycle process is a sequence of 4 steps that follow pretty much these 4 pieces of curve. And I've fiddled with it a little. I've tried, to remove the ugly. These exponents aren't exactly the 1s and the 2s that I have, up here. I've cleaned it up just to make it a little bit easier for our purposes. But this is morally very close to a very real, very important calculation that you'll be doing at some point in future thermo class. So anyway, important trick. So how are we going to do this? Well, by the way, I wish I thought of the following idea. I didn't. Somebody showed this to me. This is one of those ideas which it's hard. It would be a hard idea to come up with on your own, but I'm going to show you. Right? And so you don't have to come up with this idea on your own. You get to copy me in the same way that I copied, somebody long ago. So these ideas keep trickling down. So here's the big idea that makes this all work. Step 1, make sure that your equations are written as level sets. Make sure you've got stuff equals constant. That's a big part of this. If the algebra comes in that form already, as this is, cool. If not, move terms around, do what you got to do to get stuff equals constant. Okay. Next thing, whatever these functions are that you're setting equal to constants, make those your u and your v. We're going to see why this works in just a second here, but that's the second key step. So step 1, make sure you got stuff equals constant. Step 2, let the resulting functions on the left be your change of variables function. And notice that this does not give me x and y as functions of u and v. This gives me u and v as functions of x and y. So we're in this circumstance up here where we're going the wrong direction, right? Okay. So that said, though, here's why this is awesome, this particular move, and why it's really desirable to go backwards. It's because if I look at these curves then, let's see here. If I look at, for example, these two curves, xy equals 1 and xy equals 2, well, don't forget xy is u. So these two curves in the dark green, it just becomes u equals 1 and u equals 2, and those are straight lines. Even better than that, perfectly vertical straight lines in the UV plane. And then likewise, you can probably see this coming, but these two equations for these other two curves, xy squared equals various constants. Well, now that's become v equals those various constants, and those are perfectly horizontal lines. Right? And so what you end up with then is that my new domain over here, and it remains, we've got to figure out how to deal with some of the facts, some of the aspects of the fact that we're going backwards. My new domain is a rectangle. And again, we all love rectangles. So you can see this is a very attractive approach. We do have to talk through the details of how to do it. We'll draw the line right there for today. Y'all have a good weekend, please. And we'll finish this story and more on Monday. Have a good one.